Okay, this is lecture 2, so let me change this to lecture 2. And example 3, eigenvalues are real with different signs. So let's assume that lambda 1 is less than 0 and lambda 2 is bigger than 0. This is an example of this situation. And eigenvalues are lambda 1 is minus 3 and lambda 2 is 2, eigenvector and eigenvector. Okay, so this situation is what we have here. This is negative and the other one is positive. So let me write down the solutions of here. And let me just keep it for a few moments so you can see. Okay, so xy will be, so xy will be c1 e to power minus. Okay, so well, I chose some initial condition. Let me see what the initial condition we picked. Oh, okay, so 4 and 3. So x0 is 4, I picked x0, 4, and y0 is 3, and that gave me c1 equal to so let me write them down separately. So x will be c1 is 13 over 5 times 1 times this times 3t. c2 is 1/5 times this, that is 7 over 5 e2t, and the y is c1 13 over 5 3t, and is it plus 2/5 e2t. Okay. Again, say it. These two are like parametric equations for say a particle moving in xy plane. So treating them as parametric equations for a particle, we will get trajectories, and I in fact graphed this trajectory. So this trajectory starts at 4, 3. So first of all, this situation is interesting because it's called the saddle point, or saddle. The saddle point, we have two, in fact, like asymptotes here. So those two are, in fact, in these two directions. So the two eigenvectors give me two directions. Now this direction is 1, 1. 1, 1 is this, right? So 1, 1, that's how you find it, right? 1, 1. So that gives me direction 1, 1. And the other one is x7, y2. So there's like 7 here, and y is like 2 here. So that is like this direction. Okay, so this vector is direction 1, 1, and this one is 7. Direction of this vector is 1, 1, this one is 7, 2. And it starts at point 4, 3. So it's like, I don't know, 4 and let's say, somewhere here. And it's interesting, as time passes, it goes like this. So this is point 4, 3. So it starts at 0.43, the trajectory, and so that's the graph of this. So if you graph this thing parametrically, xt, which is this one, and yt, and from say t start at 0, and I'm not sure how far I did. You can just try say 2 for example. So from time 0 to time 2 seconds or minutes or whatever, and you can try different time, and you will see that it just moves away the other way. So that is if you start here. Now you can check different starting points, but then you have to find C1, C2. So the easiest way is just the streamlines. Streamlines are in fact those trajectories for different starting points. Or in fact, if you, I think if you use MATLAB, then you have to specify a starting point, so it doesn't graph it automatically. But Mathematica does do that, so it automatically graphs some of them. So what do they look like? So this is just for this one. This is the trajectory for the one that starts at 0.43. And it has like 2 asymptotes. It looks like a hyperbola. I don't think it's a hyperbola, but it looks like that. So it goes this way. Now you can tell, do you think this is stable? Well, again, it depends. You can look at this thing. If so this one is minus 3t, well, I will graph them, but if I only have this one, not this one, if I only have this one, say, then if C2 is 0, for example, then it's stable. Otherwise, when you add this thing to this one, then you can see it starts here, or if it starts say here and it comes up to here, if it stops here, that's okay. But if it continues, then it goes to infinity. So why does it go to infinity? It's because of this one. The e to power 2t gets large and large and large and large, and it basically kills this one. This, as t gets larger, this gets smaller, in fact. So this one just adds to both x and y and just goes away. Goes to infinity. Or it depends. It depends on these two. In fact, C1, if C1 is negative, then it goes to infinity this way, say. Okay, so let me show you the graph of the trajectories, some of them, and if you stream plot this thing, so if you stream plot for x, what was the equation? Something 4x minus 5. So for the stream plot, we need the equation 4x minus 7y. So 4x minus 7y, and the other one is 2x minus 5. And you can go x from minus 4, and y also minus 4. Depends on how much you need, although it doesn't make too much difference per use. Okay, so if you plot this, the stream plot looks like this. So let me just erase this thing. So you will see things like this. And on this side, I'm going to see which direction do they go. Yeah, this direction. So here you have things like this, and here you have things like this, and here you have things like this. So the trajectories will be And as I said, you can see that in general they are not convergent. So this is called a saddle point. So this situation is called a saddle. Okay. So the only situation where lambda is real, that we have in fact stability all the time, that is when the two lambda 1 and lambda 2 are negative. And that was, I guess, example 1. So example 1 was the two lambdas negative, and we got asymptotically stable node. So this is called saddle point, and in general it's not stable, so it goes to infinity. Okay, so let's move to eigenvalues being complex numbers. So that is example number 4. Erase everything here. That situation, I think, happens more often because that gives you vibrations and oscillation. So that is eigenvalues complex eigenvalues. So lambda 1, 2 will be something like this. Alpha plus minus I beta, right? I remember we had x and y written in some special format, so that was x and y, and it was like some C1 times some matrix times something, and then plus C2 matrix, and I will write this down in some minute. So, and this was like eigenvector in complex form. So let's see. Let me write the example I have in my notes. The example is this x prime is minus 2x plus 5 y, and y prime is minus 6. Okay, again, as I said, and I say it again, for linear systems like this, the critical point is 0, 0. So 0, 0 is the critical point. And to find eigenvalues and eigenvectors, we have the determinant of A minus lambda I will give me, that's minus 2 minus lambda. I have 5 here, and I have minus 1 here, and minus 4 minus lambda. 0. So that is minus 2 minus lambda times minus 4 minus lambda minus minus plus 5. So this is lambda plus 2, lambda plus 4. So I have lambda squared plus 6 lambda plus 8 plus 5, which is lambda squared plus 6 lambda plus 13 equal to 0. So using the quadratic formula, lambda is minus 3 plus minus, that is 3 squared is 9 minus 13, and that is minus 3 plus minus 2. Now, if you wonder what happened, where did that come from? Remember, if the coefficient b, if this b is an even number, you can write down the quadratic equation in a simpler way. So let me just remind you right here, if the quadratic is like this 2bx plus c equals to 0. So it's like 2b. So b here is 3. So if this is the situation, then it's easier to write this minus b plus minus square root of b squared minus ac over a. Now why does this happen? Because you have a 2 here, 2b, and you have 4b squared and 4ac. So 4 comes out of the radical, you get a 2 here and a 2 here and a 2 here, and they cancel out and they give you this nice formula. Now, it's amazingly good if you have an even number here and this is 1. So the coefficient of lambda squared is 1, so the denominator is 1, and you immediately find it. And because I have seen students when they don't simplify this, if they don't simplify, and then they get like something like minus 6 over say 2a over 2 or something. They don't simplify this one, and that is like a big mess. Anyway, so that is lambda. So lambda 1 and 2, both of them. And remember, we just need one eigenvector, because the eigenvectors are also conjugates. You see, these two are conjugates, and the eigenvectors are also conjugates. So let's find eigenvectors. So that was eigenvalues. Eigenvectors, so I have minus 2 minus the positive one. Remember, I used the positive one, plus 2i, v1, plus 5, v2 is 0. So over here I have minus 2 plus 3, so that is 1 minus 2i, is it? Yeah. v1 plus 5, v2 is 0. If I choose v1 to be 5, say, then v2 will be 1 minus 2i, right? So the first, oops, eigen, oh, this is not be able to use something else here. I think the book uses xc. So whatever that is, so that is in fact like x1, x2, but I don't want to use x or y or something. So so that if I put this, so this is xc1, this is xc2, and let me see, did I make a mistake here? So because that's minus, right? So if I put minus 5, right? Minus 5, then xc2 will be 1 minus 2. Okay, so and separate this thing, I have minus 5, 1, plus, remember, when you go with plus, I chose this thing, this is minus 3 plus 2i. Then I just put plus here. If I put plus here, I will get minus 2 here. Minus 2i. Okay. Then, using this, that matrix which I talked about is in fact this. So the solution, let me erase this and write the solution here. So the x and y will be x and y, some constant c1 times the matrix, this matrix minus 5, 1, 0, minus 2, minus cosine, what was that? So the lambda was minus 3 plus 2i, so that's cosine 2t, sine 2t, this whole thing, plus c2, the same matrix, minus 5, 0, 1, negative 2, times sine 2t, cosine 2t, the whole thing e to the power alpha t. So that's beta, this is alpha, and minus 3t. Okay, so let's separate the two x and y because I'm going to give an initial condition to this. Okay, so let's go back again. First you find eigenvalues and you choose the eigenvalue with plus. Use the eigenvalue with plus and find the eigenvector and use the plus here. So if you have -2 here, don't write minus and 2. Write plus and -2 inside. Then put these two as the columns of a matrix, and that is this matrix times minus cosine sine and so on. And this one C1, that one C2, and we can find C1, C2 using initial conditions. Now let me write both of them explicitly. So xt will be -5 C1, and minus is plus 5 C1 cosine 2t. This is 0, and this one is minus 5 C2 sine 2t. And the whole thing is e to the power -3t. And the yt is C1 times 1 times this minus 2 times this. So let me write it down then. I will simplify. Minus cosine 2t minus sine 2t, and plus C2 times this one sine 2t minus 2 cosine 2t. With a drop, there's minus 2 here. Then I'll check minus cosine minus 2, and 1 minus 2, and the whole thing is multiplied by minus 3. Okay, so these are the two solutions. Now, since you have already taken that exam, you might have seen when you convert a second order equation into two first order equations, then x will be this one and x prime will be this one, or y will be this one, y prime will be this one. So when you solve that, the first one is if that represents like a motion of like some spring, for example, a spring damping or spring damper system, then this one represents the motion, this one is the velocity. So that is like y, motion up, down, left, right, whatever, and this one is y prime. So in that case, if you check your solutions, you will see that whatever you find here, this one is the derivative of this. But in general case, no, it's not. But it's related anyway, but it's not exactly the derivative. So, okay, now I chose some initial conditions. Let me see what initial conditions I picked. Initial condition x0 is 5, y0. Let's see. It's too dark now. So x0 is 5. So I chose x at time 0 is 5, and y at time 0 is -3. Now, in the other situation, when you convert second order into first order, this is like initial position, this is like initial velocity. In this case, it's just a x and y, okay? Now, with these two, I found so these two gave me C1 and C2 equal. So if you just plug in at 0, you will get C1 is 1 and C2 is also 1. Well, okay, not bad. So with these two, the x and y will be what did I find here? So with these two, I will get this. So there's one here and one here, so that's, and there's one here and one here, so it's just, and that's just, so let me cosine 2t minus 5 sine 2t e to the power minus 3t. And this one is simplified, and I got this. So with these two, minus 3 cosine 2t minus sine 2t e to the power minus 3t. Okay. So with these two initial conditions, I have this solution. Now let's graph this solution and also graph the streamlines or the trajectories, all of them, and look at it. Okay. So if I plot this with a parametric plot, again, you write xt here and yt here, and and just add t from say 0 to something. And that parametric plot gave me something like this. Well, let me, so it starts at 5 minus 3, so 5, say minus 3. So it starts somewhere here. That is when t is 0. And just goes in a spiral form like this. Okay. So if you plot that parametrically, you would see something like this. And it just continues and goes round, 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 round. It's interesting, you can zoom. Well, if you zoom, you have to, if you start, say, t from 0 to say, I don't know what t was, maybe 2, I guess. Then it gives you this much. But if you continue to, say, 20, say, you don't see too much here. But if you zoom, it's like it's repeating itself. You just see the same thing. So it just goes around, comes back somewhere here, which is like this point, then goes again and again and again and again. And it never reaches point 0. Or, I mean, the origin, 0, 0. So let's graph them separately. So the parametric is, in parametric format, the time is implicit. So you don't see time over there, it's just x and y, right? So this is x as a function of time and y as a function of time. You just find, for different time, you find points and you connect them, and that is like the trajectory. If that is motion of a particle, that is how it moves. And you can tell, when this goes around this way, it's stable, right? It goes to 0. Why does it happen? Why does this happen? Let's look at these two. These are sine and cosine. Sine and cosine are not, they don't get large. They're between -1 and 1. So this part of the equation is a finite number. You can even find the maximum. You can say, okay, this is maximum, we'll say 1, this is maximum, we'll say 1. So if this is 1, this is -1, maximum will be 10. And the minimum will be -10. So we can just say that this is a number between -10 and 10. So this is not large. This is the thing that contributes to stability. If this is negative, like -3t, then this thing, as t gets larger and larger, this goes to 0, right? E to the power -3t is something like this. E to the power -3t starts with 1 and goes to 0, right? And it doesn't matter what this thing is. This gets so small that multiplied by this will give me a very small number. And I will plot these two and you will see. But anyway, the thing that contributes to stability is this. And this is because alpha is -3 less than 0. That is because alpha is negative. Okay? So with alpha negative, we get stability. And you can guess when alpha is positive, and I would just touch that one because it's something similar to this. So for alpha, it goes the other way. It starts here and goes way around and goes out and goes to infinity. So with alpha positive, this gets large, and then this trajectory just goes away and goes to infinity. So for, say, complex eigenvalues, that is in fact the alpha that decides on stability. Beta is simply what's that? The frequency. If you look at it, if you connect this thing to vibrations or oscillations, then beta is this omega t. That is like frequency, and this one is damping. That was spring mass. Spring mass damper, that -3 comes from damping. So if you have too much damping, like -10 here, then boom, suddenly it goes to 0. But if you don't have too much damping, it's like -0.0001, for example, then it goes round and round and round and round and round. It goes round and round, but it doesn't go to 0 fast, too fast anyway. So that -3 or alpha has to do with damping, and beta is the frequency. So alpha is like comes from damping, and beta is frequency. Okay, so well, you might say, what does positive damping mean? I mean that damping becomes negative because in the middle I have a positive number. Remember, the equation was like this: lambda squared plus 6 lambda plus what is that? 30. This is positive. The positive gives me negative. Positive in the middle gives me negative. Because the quadratic formula is minus b. So if this is positive and this is positive, then, and in fact in vibrations, remember this comes from the damping, the middle one. So if that is positive, which means we have damping, then this happens. So you have stability. And well, you might say, so what does minus mean? Minus damping, I don't know what physically that means, but that definitely, if there is a system that with negative here, -6, then you will get +3 here, and it will be unstable. Okay, so let me erase this thing and plot each one separately, and I have separately they so x is this one and y is this one, so x starts at the 5, and I have this picture here. If it starts at 5, and you can see that it's just too much damping, so it just comes down and just goes 0. The other one starts at -3. But with smaller alpha here, you would get some vibration. So anyway, this one goes like this. But both of them go to 0. Now, if this is small, if I have, then you might see something like this. And it doesn't get large. So it shouldn't get large, it should get smaller. So, something like this. So they both go to 0 with negative or positive alpha. If alpha is too large, then it damps like this. If alpha is small, then it vibrates and then damp. So these are these two separately, and if I plot, if I use string plot, I will get things like this. And so I will get things like this. So, and they tend go towards this 0, 0. Okay, so that is in fact the string plot. So string plot of the equation. What was the equation? Let me show you. So that is parametric plot of these two. This one is parametric plot of these two specifically. This is the string plot of the equation. So the equation was minus 2x and plus 5y and minus x minus 4y. And I just give some. Okay. So that is okay. Now, in the terminology goes like this. So that is a spiral. You see, it's spiral, and there are two different. Well, the other situation is when you have alpha positive. So let me erase this thing and give you some general idea. So without even solving the problem, you can say, okay, whatever the solution is, it's stable or unstable. So when you solve for lambda 1, 2, you will get something like this. This alpha is the damper or the damping coefficient. If alpha is negative, you will get this, something like this. They go to 0 somehow. So spiral, and the spiral, it is stable. Sometimes this is called a sink, spiral sink. It's like a sink in the bathtub. It goes round and round and round. It's like, if it is like a motion of a fluid, for example, then the fluid is just sinking, just going in. Right? So it's like going inside. And if alpha is positive, then it is spiral, it is unstable, and this is called a source. And it's just the other way around. It just goes out. And you can tell why it's called source. It's like, gee, should be interesting. It's not interesting. Okay, so. So these are, it's like source, it's like water is going out of this point. That's like a source, and boom, something is going out of this as a source. Okay, now, what happens if alpha is 0? Well, let's see, if alpha is 0, we will get something like this. So let me erase this thing, and you might say, how could alpha be 0? Alpha can be 0. And there is no damping. Remember, for a spring mass, if it is simply a spring mass, K, if there is no damping, then this x will be 1. This x is simply like some A cosine omega t. There is no e to power something. Okay? So this is when this happens, but if we have damping, say, we will get x is some A and B. Okay, so it can be, well, it might have some So it looks like this. So it will be some A, some e to the power, some alpha t, then say cosine omega t plus beta. So it has a phase shift. But that one also might have phase. Might have phase shift. Might have phase shift depending on initial conditions. This one also can have phase shift. So but anyway, it looks like this. And this one, the big difference is this. The big difference is this thing. This one looks like what? This one looks like this. So it starts somewhere and then just goes on and on and on and on. This is not, it's okay if it just goes round and round. I mean, it doesn't go to infinity, but it doesn't go to zero either. So we say that that's stable, in fact. Well, it just goes round, round, round. It doesn't go round and then like this, just go to infinity and break the whole system. This one depends on alpha. If alpha is negative, we will get something like this. Alpha negative. And if alpha is positive, it might go like this. Alpha positive. So, depends on this alpha here. And that alpha comes from that middle, say, coefficient, either in the eigenvalue, in the characteristic polynomial, or if you're dealing with the two second degree equation, then it's the middle coefficient, say, for y prime or x prime. Anyway, so this can happen. If this happens, then both x and y are functions of both sine and cosine. So if this happens, if I have alpha 0, that is one case, then I have x as a function of time. It's like some c1 cosine omega t plus some c2 sine omega t. And the other one is also something like this. So it might be some, I don't know, let's say, A, say, cosine omega t, let's say B, sine omega t, something like that. The A and C are different. So if I graph this thing, I will get in general an ellipse which goes round. So wherever it starts, say if this is t equal to 0, it goes round and round and round and round. So that is the parametric plot. That's the parametric plot of x and y. And separate plots, if I plot them separately, so that is if I just plot them, so one of them, I don't know which one, but both of them will be like this, depending on the coefficients. I don't know where they start, but depending on the starting point. So this will be like x0, say, and this will be like y0. So if this is x, and this is y, they are both like sine and cosine, and so that is the parametric form. So that t0, I have this point will be x0 and y0, point x0, y0, and is it both? I think the x is that's what I'm impacting on. X positive and y negative. Okay. So so this situation is okay, and we can have this situation, and this situation is not bad. And it can happen when we don't have damping, and if this happens, we call this thing a center. Okay? And we say that it's stable. So if we have a center, it's stable. So unstable, basic, or let's say stable happens when if the two eigenvalues are real, stable, it happens when the eigenvalues are negative. If they are complex, then it happens when the real part is negative or zero. Okay, so that is basically the whole thing. Now, the situation that we have one eigenvalue is, I'm not going really to discuss that. You can read from the book, and I said, but I haven't seen in practice like in vibration or something like that happening. I mean, it's so, when you're dealing with just random numbers, well, they're not really random, but they're not cooked up numbers. So it's hard to have a situation like that. But I don't know, maybe it happens in areas that I cannot think of. You get something like that. But you can read that thing in the book. When that happens, what we have and in which situation, you can guess that in that situation, remember you had two solutions. One was e to the power lambda t, and the other one was t e to the power lambda t, right? Or something like this. So if lambda is negative, you can tell. If lambda is negative, then this goes to 0, this also goes to 0. So for lambda negative, you have stability. And for lambda positive, definitely there is no stability because both of them go to infinity. So you can talk about stability when that happens. And in fact, if that lambda that you find is negative, then you can say it's stable. So let me stop here. So I guess I finished stability, and next time I will start nonlinear equations. And for nonlinear equations, we have to linearize them, so we have to use the Taylor series for each one of them. But I'm not going to use the Taylor series in full strength, no, just one term. In fact, two terms. And you will see that we will have more than one, say, critical point, because that's nonlinear, we have more, and then we will discuss stability for each critical point. After linearizing around the critical point. Okay, so that is it for this time, and see you next time.